I just wanted to do a short video on orbits because that comes up in some of the qualifying exam problems that I assigned. So I'll just give the definition, and hopefully, as we discuss the problems on Campus Wire this week, we can fill in more theory. But if I have G a group, a G be a group, be a group, and I'm going to think of G acting on a set A, then the orbits of G on A are subsets of A. So that's important. Here, when I was talking about stabilizers, stabilizers are subgroups of the group. Orbits are subsets of the set. Um, so of the form. So usually we use O sub A, that'll be the orbit of a little element A, G dot A for G in G. So it's basically, if you think of, your set A and it has, all these little elements in there, then you start at some element A and you act by some element G, maybe you end up here. You act by another element G, maybe you end up there. You act by another element G, maybe you end up there. But maybe there's no element G that allows you to get to this element or this element or this element or this element or this element. Then we would say, let me do this in blue, that this subset of A is the orbit of this little element A. And if, this was element B, and this was element C, and this was element D, then it is the case that the orbit of A is equal to the orbit of B, is equal to the orbit of C, is equal to the orbit of D. Because if I can find an element to go from A to B, I'll also be able to find an element to go from B to C, from B to D, from C to D, etc. So actually, I will see that with my group, I can go from any element in the orbit to another element in the orbit, but I can never leave the orbit. Then there will be, other orbits. Maybe these 2 points are in an orbit together. Maybe these 3 points are in an orbit together, and this one is alone in an orbit. And what I want to say is that orbits partition the set A, i.e., if O1, O2, up to maybe OD are the orbits of G on A, then A is the disjoint union of these orbits. Every element of A belongs to some orbit and only one orbit. So you can think of these orbits as equivalence classes. And then the action of G on A is transitive, which is a word I introduced before, but this is if and only if G has only, not also, only one orbit. So that would be the case where, remember, transitive meant that for all A1, A2, there exists G with G acting on A1 gives me A2, and then, well, this tells me that there's only one orbit because I'll be able to get anywhere from one point.